Okay, welcome to everybody that's at home because you skipped today because you were doing various things and now you're trying to get caught up in what we're missing. And today we are starting Chapter 9 on inequalities. Now before we go any further, an equality, since we're going to talk about inequalities, we're going to talk about equalities. Equalities are two expressions that have the same value. So our first definition is what an equality is. And an example of this, the most basic example, would be x plus 1 equals 3. These are two expressions, x plus 1 being an expression and 3 being a monomial expression. These two expressions have the same value. Therefore, they are known as an equality. Another way to think of it is because they have an equal sign. Right? So we've been studying in Chapter 8 all about equalities and what they mean and how to solve for missing terms within expressions. And we have techniques that we would do it. We'd subtract 1 from both sides to determine that the x value has to be 2 in order for this to be an equality. Conversely speaking, an inequality, by definition, are two expressions that may be equal and or greater than each other, greater or less than each other, greater than or less than each other. That will be the definition for what an inequality is, and we have two things. Now, you do know from your experience that this sign means less than. This sign means greater than. And your two new signs that you never saw before would be this sign. Anyone want to take a stab at that one? That's right. Less than or equal to. And the other one would be greater than or equal to. So these are, we have had experience with these before because we've used these in years past, but we've never used the other two symbols, which are greater than, less than. So if I said, for example, if I said x is less than 1, right? For those of you who struggle with how to read the symbols, I said the word x, and then the next symbol is pointing at that. It is not eating what I said. It is pointing at what I said. That's a way for you to be able to say is less than. So if it's not eating what you said, it's less than. If it's eating what you said, it's more than. So conversely, I could read this as, and I'll spell x with a, I'll spell it, no, I can't do it that way because it's there. Okay, x is less than 1. That's what it says. But if I read it backwards, I could say 1 is greater than x. See, if I read it backwards, I could say 1, right? This is one way to say it. This is another way to say it. 1, and since I said the word 1 and the symbol is eating what I said, I would then say is greater than x. Well, I could actually read that sentence two ways depending on which direction I read the sentence. If I read it left to right, it's x is less than 1. If I read it right to left, I can read it 1 is greater than the number. When I think about that, I could express my solution as a set of numbers, okay? Because it says x is less than 1, give me any number less than 1. Negative 1. Give me another number. Negative 3. And I could go forever in that direction. If I wanted to be very accurate, I would say x can be, x is less than 1. So 0, negative 1, negative 2, and then I could use this ellipsis to say that will go forever. These brackets are like, you make it by going down, a little dippy in like that. That is a set of numbers that would be relevant for x. So in this case, in inequalities, there are infinite answers. There is not one answer for this particular inequality, right? There are infinite answers. X can be infinitely defined as any number that's less than 1. So the main difference between equalities and inequalities is inequalities have many solutions. Equalities typically have one solution, typically, in our experience. Okay. Another example would be, I'll keep it simple again. X plus 1 is greater than 3, okay? For this example, we solve it the same way. So we're going to solve it the same way that we normally would. We would isolate the variable by getting rid of the constant, and we'd have x is greater than 2. So therefore, this solution says any number or all numbers or x, any numbers, all numbers, or x, depending on how you want to read it, is greater than 2. So our solution for x here is any number that's greater than 2, which would be 3, 4, 5, etc. Right? But there are also other numbers. We can say 2.3 is another number. Okay? That's another number that can be done. So expressing our solution this way doesn't allow us to express things like 2.1, 2.2, 2.5, 2.394. Those are still numbers that are greater than 2. But if I express my number as a set of numbers, I can't express all those infinite decimals that are greater than 2, but I can't write them within that set. So there has to be a different way to do that. Here's the different way. You can also show inequalities using a number line. All right? So we're going to use a number line. And I'm going to show you the solution here using a number line. So I'm going to make a number line. Since it goes in infinite directions forever, because it's not just a one-numbered pony, these little arrows here show that these number lines will go infinitely in both directions. Since my number is 2, I'm going to use 0 as my middle point. I'm going to use 1 here, 2 here, 3 here, -1, -2, -3. Okay? So there's my number line. And I want to show all numbers that are greater than 2. Okay? So my solution, Riley, can the number 2 be a number that fits in that solution for all numbers greater than 2? Is 2 a number greater than 2? Yeah. Are you sure 2 is greater than 2? It's not, is it? Because Claire, what is 2? Is 2 the same as 2, or is 2 greater than 2? It's the same, so it's not greater, it's the same. So it's equal to. So we cannot include the number 2, right? So mathematically speaking, if the number that we're starting on is not a part of the set of the solution, so 2 can't be a number because it's not greater, what we do is we use what's called an open boundary. An open boundary. Boundary, B-O-U-N-D-A-R-Y, boundary. An open boundary is where it starts, okay, but it does not include the number 2. So if it's open, it does not include. If it's closed, it does include. We'll talk about that in a second. But any number from that point forward to infinity, on that red line that I just drew with the arrow, any number that exists would be a number that is greater than 2, right? Including right here. What would that number be right there if I put a little dot there? 2.5. What would this one would be here? Right. What about this one here? Whatever, right? You got the idea. So any number on that red line from this point all the way to infinity are numbers that are greater than 2. Sure can. So again, an open boundary means the number it starts on, or the number it's on, is not included in your set. Okay, is not included. An open boundary, when we use it, it means it's not included. And as we can see here, 2 is not one of our solutions, so it's not included in the set of numbers that makes x possible. If I look at another example, and I'm going to give you one of those other 4 symbols that we use. If I go x plus 1 is greater than or less than, let's just do 5 this time. Oh, x plus 1. Let's do x plus 1 is greater than or equal, let's go less than or equal to. Less than or equal to 5. We wrote that, okay? So there's an inequality, right? We have an infinite set of values. The difference between our two examples is this symbol means less than or equal to. It's both. It's less than or equal to. So I'm going to solve it the same way that I would algebraically, and I get x. All numbers less than or equal to 4 is my solution. Right? If I graphed my solution on a number line, I'm going to put 0, 1, 2, 3, 4, 5, 6. I'm just going to make that my number line. Okay. And I read this as, my solution says, my answer, it says all numbers, or x, less than or equal to 4. Okay, that's what it says. That's what my solution says right here. All numbers less than or equal to 4. If I was to draw my solution set, it would be 4, it would be 3, it would be 2, it would be 1, ... to infinity. Those are all numbers that are less than or equal to 4. And notice here, 4 is in my set because it can be equal to as well. Okay. When I graph that solution, Chloe, one more time, am I using an open boundary or a closed boundary? Because 4 can be a part of it, I'm going to use a closed boundary. So I'm going to take my 4, and instead of using an open circle like I did here, I'm going to use a closed circle. That means that it starts at 4, and 4 is an included number in that valid set. And any number less than that, meaning my arrow goes this way, is a value of x that would make this inequality true. Just to prove my point, if I chose 0, which is on that line, and I take my inequality in its original form, as my original form inequality before I isolated the variable. If I choose any of these numbers, and I'll just choose 0 and substitute it, right, 0 plus. The solution looks like this. 1 is less than or equal to 5, and that's true, right? So 0 is a possible number for x that would make this inequality still true, right? And I could choose any of those numbers. I could choose 3, I could choose 2, I could even go over here and choose -8. And no matter which number I choose on that infinite red line, it would be true for x plus 1 is less than or equal to 5. Okay? So those are two examples of very simple inequalities. Now, let's talk about something else. So if I had this, let's try this out. Go ahead and see if you can solve this and graph the solution. Okay? Go ahead and try it. Here's what I want you to do first. Write it in words. See if you can do that first. Write it. What does this say in word form? Then solve and write a set of solutions and a number line. Okay, see if you can do that. Go ahead now and try that. All right, that's enough time to think about it. There's two ways to write it in words. You could say 2 times a number, or 2 times x, or 2 times a number, is greater than 3. That's one way to read it. Or, I like this one better. Doubling a number is greater than 3. Right? Or you could say 2 times x is greater than 3. Those are, either one of those sentences is accurate enough to say what this says, right? And what would be the difference if I put this line here? How would that change the sentence, Bree? If I put that red line there, how would it change it? You would say 2 times a number is greater than or equal to 3, right? But it doesn't. It just says it's greater than. So we'll just leave it like that. So when we solve the solution, we are going to take our inequality, and we are going to divide both sides by the coefficient. And we will solve it to say any number that is greater than 1.5, any number greater than 1.5, when placed here, would make that inequality true. So give me any number, Riley, that's greater than 1.5. Any number. 1.6, right? So if I substituted 1.6 here, what would that value be? 3.2. And is 3.2 greater than 3? Yes. So 1.6 is a valid value of x to make this expression greater than this expression. 1.6 times 1.6? 1 times 1 is 2. 1.6 times 1. I think so. Now, what does that look like as a set? Any value. 1.5, 1.6, 1.7, dot, dot, dot. Any of those numbers in the set are valid. That would be a set of numbers. Any of those sets. The ellipsis, that's called an ellipsis, E-L-I-P-S-I-S. An ellipsis means it goes on forever. You use it in writing as well. And when I do my number line, if I put 1.5 in the middle, put 1 here and put 0 here, and put 2 here and 2.5 here, put my arrows here. There's my number line. Chloe, is my boundary point an open boundary point or a closed boundary point on this number line? Is 1.5 a number that it can be or can't be? It can be 1.5 or can't? I can't. What would you say? It can? If I put 1.5 here for a value of x, is this red statement true? 3 is not greater than 3, correct? So the value of x cannot be 1.5. It has to be greater than that. So because it can't be it, but it starts at it, we use what's called an open boundary. That's where my values start, but it does not include 1.5. But any value greater than 1.5 would be any number that starts on that open boundary point and fits on that red line, correct? So if I asked Riley again, Riley, what is this green dot right next to that 1.5? What would you guess? How about 1.51? Would you guess? Would that be okay? So 1.51 is a number that's not starting at 1.5, which is really, if I zoomed in, I could have 1.51. And if I substituted 1.51 as one of the values of x, then I go 2 times 1.51, which will be 3.02. And 3.02, which was the value of this expression if it's 1.51, 3.02 is greater than 3, so therefore that is a potential value for x. But there are infinite values, okay? Now, given all of that information, there is only one extra additional idea that I have to share with you. And this is the, we're going to call this the important fact. When isolating the variable in an inequality, when isolating the variable in an inequality, if you multiply or divide by a negative number. This is the most important fact of the whole chapter right here, what I'm about to write. You must, double underlined, flip the inequality sign. Okay, that's your most important fact for this chapter. If you can remember that, you will never make mistakes and you'll get 100% of the exam, I guarantee it. So if we had a very simple one, I'll just give you one here. 2x is greater than, let's go 6. Okay. So this says a number multiplied by negative 2, a number multiplied by negative 2 has a value greater than 6. Riley, mental math, don't solve it, just give me a number you think would work for that one. What's a value of x that makes that true? Negative 4 is the one I thought of too. So if you substitute it in your head and say, okay, negative 2 times negative 4 is greater than 6, is this true? Yes, because this becomes a positive 8, because a negative times a negative is a positive. So negative 4 is one value, right? What about negative 3? Is negative 3 a valid value? Bree, what about negative 3? Is negative 3 going to make, if I substitute negative 3 for that x, will that make that expression greater than 6? If I put negative 3 for the x. No, it would make it the same. So negative 3 is not one of those numbers. But Riley was right in saying negative 4. Bryn, give me another number. Negative 4 is 1. Give me another number that would work in there to make that greater than 6. He said negative 4, and he's right. Negative 5. So if I substitute a negative 5 for x, I get a positive 10. And a positive 10 is greater than 6. So we now have two numbers. We now know that our set is going to be negative 4, negative 5, negative 6, ... forever. Any of those numbers are values of x that would make the expression negative 2x have a value greater than 6. Now here's the tricky part. If I isolate it, what would I do to both sides here? How do I isolate negative 2x is greater than 6? What would I do if this was an algebra? What would you do if it was an equality and not an inequality? How would you solve this? Algebraically speaking, what would you do to both sides? Divide by negative 6, that's right. You would divide both sides by negative 6. So even though it's an inequality, we're still going to solve it the same way, so we'll try this. We're going to divide both sides by negative 6. And I have a solution, negative 2, yeah? Sorry, I said divide both sides by negative 2, right? And 6 divided by negative 2 is negative 3. So my solution looks like it should work. But when I read it, it says all numbers greater than negative 3. And are these numbers greater than negative 3? No, they're all the opposite of that, right? Every one of those numbers is a number that's less than negative 3, not all numbers greater than negative 3. So there's a mistake that happened when I isolate it. And if you follow this rule here, it self-corrects the mistake that happened here. So because I divided both sides by a negative value, in inequalities, what you're supposed to do is take this sign and flip it. Okay? And in doing so, you've righted the ship. You've balanced the math here. Because now it says all numbers less than negative 3, and this set clearly says all numbers less than negative 3. So now it's perfect. So because you divided or multiplied by a negative value, the only thing you have to do in addition is flip your sign. So, Chloe, what number am I going to put in the middle for my number line? What would you do? What would you put in the middle? If it says all values less than negative 3, what's a good number to put in the middle? Negative 3. And then I'd put negative 4 here, and I'd put negative 2 here. There's my number line. Okay. Riley, open or close boundary point? Open or close boundary point for on that negative 3? Why? No, because negative 3 can't be one of those numbers that makes this true. Because if I substituted a negative 3 there, this is not greater than this. It's the same. So negative 3 can't be one of your numbers. So I have an open boundary. Trickier question, Chloe. Which direction does it go? Does it go left or does it go right? For all numbers less than negative 3. It goes left, correct. Because is this a number that is less than negative 3? No. So it has to go this direction. Okay? Does that make sense to everybody? Kind of, sort of? Kind of, sort of, maybe? Okay, let's try this one. So here's another example. X over negative 2 is greater than or equal to 4. So write that in words to start. And then what I want you to do is solve it. Create a set of values that it's potential for. So a set of values that are valid. And then make a number line of your solution. See if you can do that. So again, when you have x, don't say x from this point forward in inequality. Say all numbers. Right? use the words all numbers instead. So our solution for this would be in word form. Sorry, I hope you press pause. Is all numbers divided by negative 2 is greater than or equal to 4. That's what this whole thing says. All numbers divided by negative 2 is greater than or equal to 4. Okay? That make sense so far? Yeah? So how many values are there for x? There's infinite values. So we're going to solve it. We're going to write our inequality. And we're going to solve it. So what are we going to do to isolate the variable here, Tatum? Right. I multiply both sides by negative 2. Right? Now, if I follow that rule that you wrote in red right here, that important fact, which I can't get to for some reason. There it is. When isolating the variable in an inequality, if you multiply or divide by a negative number, you must flip the inequality sign. Well, in isolating, I am multiplying both sides by a negative value. So I've isolated x, but I have to flip this sign. So I'm going to flip it to this. And my solution for this particular inequality would be any number that is less than or equal to negative 8. All numbers less than or equal to negative 8. Does it include negative 8, Riley? Does it include negative 8? Is negative 8 one of the values that's possible? Yeah. So in my solution, I'm going to go negative 8 as my starting point. All values less than or equal to, then I go negative 9 and negative 10, and then 3 little dots, and we're off to the races. That is the set of values that shows potential values of x to infinity. On my number line, all values less than or equal to negative 8. I'm going to put negative 8 in the middle. I'm going to put negative 9 over here and negative 7 over here. Madison, is it an open boundary or a closed boundary for this inequality? Say it again. It's not open, it's closed, because the reason why you had a 50-50 chance you screwed that one up is because of this line right here. Okay? That means or equal to, right? So any number that's less than or equal to negative 8, which means 8, negative 8 is a possible solution, just like in here. Negative 8 was a possible solution. I'll show you again. If I substitute negative 8 here, if I substitute the value negative 8, I'll end up with an expression that says 4 is greater than or equal to 4. Is that true? Yes, because it has that or equal to part. 4 is equal to 4, and therefore negative 8 is a potential solution for that inequality. I'll go back and erase that. So therefore, I use a closed boundary point. And any number less than or equal to that means my number line goes this way. Okay?